Well, although symbolic integration is a challenging subject that will stay with us throughout our investigation of calculus from here on out, we are already at the point where we are going to look at the last of the standard integration methods, which is integration of rational functions using partial fraction decompositions. And integration with partial fraction decompositions has two sides. On one hand, there is good news, which is we will know exactly when we need to use partial fraction decompositions, and we will know exactly how to apply it, so there's no guesswork. The downside, however, is that partial fraction decompositions, by their very nature, can become a little bit tedious. Let's take a look at how we're doing these partial fraction decompositions. All right, so basically the idea is that, well, we know that polynomials, which are just sums of products of x's with numbers, or powers of x's with numbers, those things are easy to integrate. And the next more general class of functions are rational functions, where we still use x's and powers of x's and multiplication with constants and addition. But in rational functions, we also allow a division, right? So a rational function is just a quotient of two polynomials. These things are therefore natural generalizations of polynomials, and they occur pretty frequently in applications too. So we are interested in the integrals of these rational functions for that reason, and also, and maybe more importantly actually, the method that we're going to use to integrate these functions, which is partial fraction decomposition, that method is also very important when we're solving differential equations with Laplace transforms, which probably is on tap for you sometime later in your course sequence. So, we're starting with theoretical background. We will see plenty of examples. All these sections are examples here. But you can also further your mathematical education by first looking at the abstract theorems and trying to make sense of them. So the first theorem that we need as background is the real number version of the fundamental theorem of algebra, which says that every polynomial with real coefficients can be factored into factors of the form x minus c to the n and x minus a squared plus b squared to the n, where these n's don't have to be the same exponent. So that basically is the fundamental theorem of algebra, which was talking about complex coefficients, and in complex coefficients you can then turn everything into linear complex factors. And by the conjugate pairs theorem, when you've got real coefficients, any two complex zeros occur in pairs, and when you take in conjugate pairs, and when you take factors that come from conjugate pairs and pair them up, you're going to get exactly something like this. Now that is something that you can try to work through, or at this stage we might as well also just take it. It does always work, and we are not going to take a significant detour into complex analysis here. So basically what that means is these denominators in the rational functions, the denominators that make rational functions different from polynomials, those things can be broken down into factors that are potentially simpler. Now the other thing is that partial fraction decomposition allows us to do the following with every rational function with real coefficients. As long as the degree of the numerator is smaller than that of the denominator. Okay, so every rational function with real coefficients so that the degree of the numerator is smaller than that of the denominator can be written as a sum of terms of the following form. On one hand, for all the factors in the denominator that are of the form a x minus c to the n, we generate a term a over x minus c to the n. And for all the factors that are of the form x minus c squared plus b squared to the n, we generate a term ax plus b over x minus c quantity squared plus b squared to the n. Every rational function can be written as a sum of terms of these forms, and in each case this exponent n runs from 1 to the exponent that the respective denominator has in the factorization of the function's denominator. Okay, now that looks rather complicated. We will see in the examples how that lines up. Basically what you want to remember is that you can break it down into terms that look like this, and what you have to do is you have to count in the exponent from 1 to however many terms of each form you have in the denominator. Okay, so but basically what that then means on the theoretical side is that if we can somehow integrate functions that look like this or like that, and if we can find a way to write out the decomposition, and that's what most of our examples will be about, well, then we can integrate rational functions. So we need the integrals of the rational functions that cannot be further decomposed, and we have those. We will omit the integration constants in this proposition. And, well, most of these integrals can be memorized, or I would prefer really if you understand substitution and antiderivatives well enough, you can see most of those integrals, and we'll talk our way through how those integrals come up right here too. Namely, the integral of 1 over x minus c, well, that's the natural logarithm of x minus c, right? If you want to do the step-by-step process, you would do a substitution u equals x minus c, dx is du, you get ln u, and then you get ln of x minus c. So that's not that bad. And it may be good practice to just write that out on a piece of paper to make sure you understand what's going on there, because this is the kind of stuff that ultimately can be very helpful if you can just do that instinctively. The factors then ultimately that are of the form 1 over x minus c to the n with n greater than 1, well, those are integrated with the power rule, right? It's the same idea. You do a substitution u equals x minus c, and then you've got u to the minus n, and with the power rule, you get that the exponent is negative n plus 1, which is 1 over u to the n minus 1, and you get a 1 over negative n plus 1 there, which is the same as 1 over negative quantity n minus 1 here. So those are the antiderivatives of the linear factors. We're coming to the quadratic factors, and well, there are some that are easy as long as you remember the right antiderivatives, because here, remember that the antiderivative of 1 over 1 plus x squared, that's the arctangent, that's the inverse tangent. And so if you just factor out a b squared in the denominator, you end up with 1 over b squared, 1 over 1 plus x squared, then 1 over 1 plus x over b quantity squared. You do a substitution, u equals x over b, and here is what you get on the right side. Again, this is something that you may want to write out, because this is the kind of thing that you, I'm not really sure if you want to memorize that, because the computation can be recovered fairly quickly. Okay, now this one, I'm not sure if I want you to write that out or memorize or so, because this is the ugly part. When you've got a 1 over x squared plus b squared raised to the n, you can't really write down the integral directly. What we've got here is what people call a reduction formula, and this reduction formula is done with a couple of, I guess, more or less dirty tricks using integration by parts. So this is a beautiful exercise, but it's a lengthy exercise, and so if you ever have to integrate something like this, that's probably something that, unless your teacher really tells you you ought to have that memorized, that's definitely something you want to look up. And again, it works for n greater than 1, because for n equal to 1, for 1 over x squared plus b squared, we have a direct formula. That leaves us with, remember that these quadratic terms are set up with an ax plus b. That means a b over this thing works out fine. And here we have an x over a quadratic, and that one again is simple, because if you just substitute the whole denominator, u equals x squared plus b squared, you end up with du dx being 2x, and that substitution goes straight through, and what you get is your antiderivative is 1/2 ln x squared plus b squared. And whoops, pressed the wrong button. And finally, you also have to be able to do that for x over x squared plus b squared to the n. Same substitution, u equals x squared plus b squared, and you can see it works out pretty much in the same pattern, right? You've got the minus in the same place. You've got 1 over n minus 1, because you're doing a power rule essentially. The 1/2 comes from the substitution, because you've got a square, and then you just have whatever you substituted inside what you've got from the power rule. Okay, another thing that you can do right here in order to verify that these formulas are correct. And again, we are also still in the practice of practicing integration as well as differentiation. You can verify at least 5 of these formulas, namely 1 through 3 and 5 and 6, very quickly by differentiating the right-hand side. And so if you want to practice that, preferably in your head, hit the pause button right now and just work these things through. I mean, it can't be that bad, right? The derivative of ln x minus c is 1 over whatever is inside, which is 1 over x minus c, times the derivative of the inside, which is 1. And now here you can accuse me that I just do the easy ones and leave the hard ones to you, but this one isn't that much different. That one is okay, except that you have to work with all your multiplications. This one isn't that bad either, and this one isn't that bad either. Okay, that was, and okay, this one again for n greater than 1, because for n equal 1 we've got this other formula in number 5. Okay, enough with the abstract stuff. We now look at concrete examples to see how this abstract stuff lines up. So typical problems here are of the form: compute the integral, as we've always done so far, of the function x plus 9 divided by x plus 3 over x plus 4. Now, the first thing is, anytime you see an integral of a rational function, partial fraction decompositions are the only thing that's going to help us, so we automatically default to this. So this is not something where we have to think about, do we use this method, do we use that method? It's always the same method. The setup is partial fraction decomposition, and here's where we're starting to make sense of these theorems that we had earlier on. So our function is x plus 9 over x plus 3 times x plus 4. We already have a factorization in the denominator, which is great. So what we know is we must have something divided by x plus 3 plus something divided by x plus 4 on the right-hand side by that theorem about partial fraction decomposition. So we get that this left-hand side must be equal to a number divided by x plus 3 plus another number divided by x plus 4. We know by theorem that that works. So there are these numbers, we just have to find them. And so how do we find these numbers? Well, we simplify and try to get better equations for a and b. First step towards that is, and that's also the first step as we are resolving the partial fraction decomposition setup, we find a common denominator, which is of course x plus 3 times x plus 4, and we just basically expand the first one with x plus 4 over x plus 4, and the second one with x plus 3 over x plus 3, and then add the fractions together. Now we've got common denominators here, which really don't help us, so we multiply by x plus 3 times x plus 4, and that means we have x plus 9 equals a times x plus 4 plus b times x plus 3. Now we have two possibilities. On one hand, we could sort the terms and set up a system of equations for a and b, which must be true because this equation must hold for every possible value of x. Well, there is another realization, and it's a realization by a mathematician slash physicist named Heaviside, who did a lot of really good work, I think mostly in electrodynamics in the late 19th, early 20th century, if I remember correctly. And so apparently this gentleman realized, hey, if this works for every value of x, it must also work for values of x that are really convenient, such as values of x that make the other coefficients go away. So for example, if I choose x equals minus 3, well then I get minus 3 plus 3 here, and that means the b is gone. And that means I directly get a equals 6. How do I get that? Well, this is a mental substitution. Minus 3 means that the stuff with b goes away. X equals minus 3 gives me a times 1 here, and I get minus 3 plus 9 on the left side, so I get a equals 6. So this is very, very lucky, of course. This is a problem that works out very easily, but for a first example, that's probably not so bad. On the other hand, you can then also guess already that the other choice has to be x equals negative 4, because that makes the term with the a go away. And so no matter how ugly the numbers are, and we will see stuff with uglier numbers too, we have b times something equals something else. In this case, we would get b times negative 1 is equal to negative 4 plus 9. So negative b is 5, which means b is negative 5. And so that means that our original function, x plus 9 over x plus 3 times x plus 4, is actually equal to 6 over x plus 3 minus 5 over x plus 4. And we can use that now in solving the integral, because now we just say that the integral of our function is the integral of 6 over x plus 3 minus 5 over x plus 4. And these are easy integrals. We get 6 times the logarithm of x plus 3, because, right, our integrand is 6 times 1 over x plus 3. And the antiderivative of 1 over x plus 3 is ln x plus 3. Minus 5 times ln x plus 4, same principle. We've got a minus 5 as a coefficient. And the antiderivative of 1 over x plus 4 is ln of x plus 4. We put the mandatory plus c for the indefinite integral in the back. And we already have the problem solved. In some ways here you have already seen most of the process. It's entirely computational. The only thing that can happen is that the computations can get worse. Now, next thing we're going to look at is what happens if our numerator has a higher degree than the denominator. So if we, for example, want to compute this integral 6x to the 4th minus 7x cubed plus 8x squared minus 10x plus 1 divided by 2x squared plus x minus 3, well, that's certainly not one that you want to try to do in your head or anything like that. That's definitely a paper and pencil kind of problem, because we'll have to keep track of a lot of numbers. On the other hand, however, it is not difficult in principle. We know integration by integration with partial fraction decompositions will take care of things as soon as the degree of the numerator is less than the degree of the denominator. That's not the case here, but we know what to do for that. If we have a numerator whose degree is higher than the degree of the denominator, the first thing we do is we just divide, because we can rewrite this rational function as a polynomial part plus a rational function part that is of a form that we can decompose. So we take our numerator and we divide it by our denominator, and you know, or you're supposed to know, how we divide polynomials. So this is something that we have to dig out from way back when in algebra. Well, let's see. We're always looking at the leading terms, right? 6x to the 4th divided by 2x squared is 3x squared. So the division gives us a 3x squared. And now we take 3x squared times the divisor and subtract that off the numerator here. So 3x squared times 2x squared is 6x to the 4th. 3x squared times x is 3x cubed. And 3x squared times negative 3 is negative 9x squared. And we want to subtract that. And this is the way I keep track of things. I write down the numbers as I get them from the multiplication, and then I remind myself I have to subtract them all. That way I don't have to cross out anything here and potentially have to remember, well, did I cross something out here or not? I'll just put a negative sign out front and work out the rest. And so here 6x to the 4th minus 6x to the 4th, well, that's nothing. And then negative 7x cubed minus 3x cubed is negative 10x cubed. 8x squared minus negative 9x squared is plus 17x squared. And then it's always, or it's potentially a good idea to just keep track of the remaining terms, right? Negative 10x has nothing subtracted, 1 has nothing subtracted, so we just pull those terms down. Okay, so now negative 10x cubed divided by 2x squared, that should be negative 5x right here. And now negative 5x times 2x squared is negative 10x cubed. Negative 5x times x is negative 5x squared. Negative 5x times negative 3 is plus 15x. We again subtract everything. And as we work that out, well, negative 10x cubed minus negative 10x cubed goes away. 17x squared minus negative 5x squared is 22x squared. Negative 10x minus 15x is negative 25x. And we keep the 1 from what we had previously. 22x squared divided by 2x squared should give us 11. And that gives us 11 times 2x squared is 22x squared. 11 times x is 11x. And 11 times negative 3 is negative 33. And again, we subtract it all. And what we get is 22x squared minus 22x squared goes away. 25x minus 11x is negative 36x. And 1 minus negative 33 is plus 34. And that means that our function now, which was this big old rational function, I don't need to read that to you, it's equal to the polynomial part, the 3x squared minus 5x plus 11, plus the remainder, negative 36x plus 34, divided by the denominator, 2x squared plus x minus 3. And so now here we've got a part that we know how to integrate. Here we have a part that we know how to integrate, but it's not decomposed far enough. So the next thing is a partial fraction decomposition of negative 36x plus 34 over 2x squared plus x minus 3. First thing we need to do is we need to factor the denominator, and that's something that I am quite terrible at, but let's see, this would be something like, oh goodness, 2x minus 1 times x plus 3 or something like that. Well, actually the other way around. 2x plus 3 times x minus 1. Well, let's see, 2x times x is 2x squared. 2x times minus 1 is negative 2x plus 3x gives us x, and 3 times negative 1 gives us the negative 3. Right. That's another one of those paper and pencil kind of things. If you've seen more of my presentations, you know that I use the quadratic formula to solve stuff like that, and then I could just reverse engineer this stuff too. Alright, so that's the factorization. That was the part that in the first example we also had omitted just to focus on the decomposition itself, but here now, basically here you've got the real deal. You also have to do the factorization. Now we've got the setup, and what do we know? We know that for this one we need a term a over 2x plus 3. For this one we need a term b over x minus 1. And well, now we multiply by the denominator, and I've already done that here. So if I multiply by 2x plus 3 times x minus 1 on both sides, of course on the left side I just keep the numerator. On the right side, if I take a over 2x plus 3 and multiply it with 2x plus 3 times x minus 1, the 2x minus 3 cancels, and we keep the a times x minus 1. And similarly, b over x minus 1 times 2x plus 3 times x minus 1, the x minus 1's cancel, and we keep the 2x plus 3. And now we already are working with Heaviside's method. And let's see, I mean, my first choice for x would be x equals 1. Yep, and that's also what I did when I set up the slides. But now the computation is a little bit uglier, because now on the left side we get a negative 2. On the right side we get a times 0 plus b times 5. Okay, so that gives us b equals negative 2/5. Not necessarily pretty, but you can see we can get these numbers. The next choice for a value of x would be, let's get an ugly, negative 3/2, right? That would make things go away here. Yep, x equals negative 3/2. And that means that on the left side we get, well, the negative goes away. 36 divided by 2 is 18. 18 times 3 is 54. Would that really become 88? Yep. And it's negative 88. That should be plus 88. Hang on here. Yes, indeed, it was not a negative 88, but a plus 88. On the right-hand side, the negative 3/2, of course, makes the term with the b go away. And if you put negative 3/2 in here for x, you get negative 5/2 as the factor in front of the a. And now that number gets rather ugly, but again, we can compute it, because now if I just multiply this with negative 2 over 5, I end up with a being negative 2 times 88, which happens to be 176, divided by that 5. Alright, so that means that our rational part that remains after we did the division is equal to negative 176 over 5 times 1 over 2x plus 3, because that's where we have the a here. And by the way, for a partial fraction decomposition where the terms get rather complicated like they do here, it is very much advisable to just keep the coefficients in front of the rational function. And then we have minus 2/5 times 1 over x minus 1, because negative 2/5 is the b, times the 1 over x minus 1. And again, notice here, this is just something that helps with the bookkeeping. You keep the factors, which we're going to have to pull out of the integral anyway, you keep the factors separate from the functions. Alright, so now we can actually compute the integral, because we know that this big rational function is equal to the polynomial part, 3x squared minus 5x plus 11, plus the remainder part, which decomposes into the integral of 3x squared minus 5x plus 11 minus 176 over 5, 1 over 2x plus 3 minus 2/5, 1 over x minus 1. And when we integrate that, well, the antiderivative of 3x squared is x cubed. Antiderivative of negative 5x is negative 5/2 x squared. The antiderivative of 11 is 11x, of course. Now it gets interesting. Here we keep a negative 176 over 5. We will get a logarithm of 2x plus 3, but because we would have to do a substitution u equals 2x plus 3, we get an extra 1/2 here. So we get negative 176 over 5 times 1/2 ln 2x plus 3. That's a good exercise with the u substitution to work out for yourself also where that factor 1/2 comes from. And that's mainly because these kinds of substitutions ultimately are considered to be very routine, but the only way they become routine is by practicing them. And of course then we have a minus 2/5 times logarithm of x minus 1, and we've got the ubiquitous plus c. And then we can simplify a little bit. We copy everything except that 176 divided by 2 is 88. Everything else is the same. And that finishes out the problem. All right, so now let's see what happens when you have multiple zeros, meaning what happens when you have zeros that are repeated zeros. I should probably call that repeated zeros rather than multiple zeros, but now I've had that headline here for long enough, we might as well keep it like that. So, solve this integral of a rational function. Well, what do? Because space is going to get a little bit short, I'm going to call this whole term f. But of course, the main thing that we have to do is a partial fraction decomposition. And that means we set that up as follows. Let's work it out backwards. Because of the x minus 2, we must have a term number divided by, because of the x plus 2, we must have a term number divided by x plus 2. Because of the x minus 1, we must have a term number divided by x minus 1. Because of the x squared, we must have a term number divided by x squared. And now, if necessary, look at the slides or scroll back in this presentation, go back to the background. When you have a repeated zero, what you must do is you must set up terms for every power of that term here. So basically, the mother term we have is an x. And we set up a over x plus b over x squared until we hit the power to which that term occurs in the denominator. So if this had been an x cubed, I would have had to set up a over x plus b over x squared plus c over x cubed, and then this would have been a d, and this would have been an e. So the repetition goes up to the power that occurs in the denominator here. So the big thing here really is the setup. Once you've got that, we just go back and do the partial fraction decomposition as before, which means the next thing that happens here is that we multiply by the denominator. And as we multiply by x squared times x minus 1 times x plus 2, on the left side, of course, everything cancels, and we keep the x plus 3. If I multiply a over x with this denominator, one of the x's cancels, but we keep the other one, so we have a times x minus 1 times x plus 2. If I multiply the b over x squared with this denominator, the x squareds cancel, and the x minus 1 and the x plus 2 stay with us. C over x minus 1 times the denominator, the x minus 1 cancels, and we keep a c x squared x plus 2. And a d over x plus 2 multiplied by this denominator cancels the x plus 2 and keeps dx squared times x minus 1 here. And now we're back to Heaviside's method. First thing I would want to plug in is probably, again, x equals 1. Actually, we start with x equals 0. Well, that's just as well. So what happens? When x is equal to 0, I have a 0 here, I have a 0 here, and I have a 0 here, which means all I keep is the term with a b times negative 1 times 2, and on the left side 0 plus 2 is 3, and that gives us b equals negative 3/2. Now we plug in x equals 1, well, we get a 4 on the left side. With the 1, we don't have anything for a, we don't have anything for b, we get something for c, namely c times 1 squared times 3, and for d we don't get anything, and so that gives us c equals 4/3. Again, you can see here, even though the numbers aren't terribly pretty, we get them. And then the last one, where I want to plug in directly, is probably x equals 2, right? X equals negative 2, of course, sure, because I wanted stuff to cancel. And, well, negative 2 plus 3 gives us a 1 on the left side. We don't get anything from the a, we don't get anything from the b, we don't get anything from the c, But if we plug negative 2 in here, we get d times negative 2 squared times negative 2 minus 1, which is negative 3. And so that would be d equals negative 1/12. And here is now a deviation from the stuff that we did as long as the zeros were single zeros and not multiple zeros. And that is that now, no matter what we plug in, we will always have several terms survive. And so now basically you want to choose a number conveniently, and then you also have to use the other coefficients. So what I did here was I used x equals negative 1, just a number for which the computations work out nicely. And we get negative 1 plus 3, which is 2. With x equals negative 1, I get a times negative 1 times negative 2 times 1, which is a times 2. Then I get b times negative 2 times negative, and b is negative 3 halves, so I get negative 2 times negative 3 halves is plus 3. I get c times 1 times 1, so that just makes me plug in the c, which is 4/3. And I get d times 1 times negative 2, and negative 2 times d, negative 2 times negative 1/12 is 1/6. Okay, now I have to work out these fractions, which can't be that bad. We just have to get it right. So let's see, we would have that 2a is equal to negative 1, negative 7/3, negative 15 over 6. No, it's a little bit different than that. Okay, let's see how we get a equals negative 5 over 4 here. 2 minus 3 is negative 1. Minus 4/3 is negative 7/3. Negative 7/3 is negative negative 21. Ha! Negative 20. Oh, brother. Sorry about that. Okay, I've just pulled up my sleeves. Let's do this one more time. I keep saying we ought to be able to do this in our heads, so let's do this. 2 gives us, when we subtract the 3, we get negative 1. We get negative 7/3. Negative 7/3 is negative 14 over 6. We get negative 15 over 6, and negative 15 over 6 is negative 5 over 2. Divided by 2 is negative 5 over 4. See, this can be done. If you use paper and pencil for that, or a calculator, I probably wouldn't blame you for that. But we move on. So after all this mental arithmetic, we have all the coefficients we need, and what we get is f, and basically here I didn't have enough room, so our function is a, which is negative 5/4, times 1 over x, right? Plus b times 1 over x squared, well, 1 over x squared is here, and b is negative 3 halves. Plus c times 1 over x minus 1, and c is 4/3. Plus d times 1 over x plus 2, and d is negative 1/12 here. Okay, we now solve the integral because we know that our integral of this rational function is the integral of this lengthy sequence of terms that is just copied straight from the other slide, and now we integrate. We get negative 5/4 times ln x, because that's the antiderivative of 1 over x, plus 3 halves times 1 over x, right? Because when you integrate 1 over x squared, you get negative 1 over x, and so the two negative signs cancel. Plus 4/3 ln x minus 1, no problem there. Minus 1/12 ln x plus 2, and we've got the ubiquitous plus c, and we're done again. Okay, so aside from computations getting uglier, there's really not much happening here, and that's also not going to change when we have complex zeros, but we also want to look at that, because when we want to compute an integral like 1 over x squared plus 1 times x plus 3, well then here we have a term that doesn't factor any further, which means here's where we have to use the setup with the ax plus b in the numerator, if you recall from the theorem from the background. I should also say here that electrical engineers, as well as more often than not physicists, are quite cold-blooded here and often just do the whole decompositions with complex numbers also in the denominator. Works just as well, gets you the result in complex form, however, which is a little bit intimidating at first. And because we're doing the calculus of functions of a real variable, we're not going to go in that direction. Instead, our partial fraction decomposition will be that we set up our function to be equal to something divided by x squared plus 1, but because this is a quadratic term that we can't decompose any further, we have to set that up with an ax plus b in the numerator. And then the linear term, of course, just gives us still a c over x plus 3. And again, we do the same thing as we always do, which is we multiply both sides with the denominator. So if you multiply both sides with x squared plus 1 times x plus 3 on the left side, you keep a 1. And on the right side, well, you multiply ax plus b over x squared plus 1 with this denominator. The x squared plus 1 cancels, the x plus 3 stays. And when you multiply the c over x plus 3 with the denominator, the x squared plus 1 stays, and the x plus 3 cancels. And, well, now I think we're going to do the same thing as before with a Heaviside type method, namely, with x equals minus 3, well, the ax plus b actually goes away, right? So that means we get that 1 is equal to 0, plus negative 3 squared plus 1 is 9 plus 1, 10 times c. So 10 times c is 1, and c is 1/10. When you plug in x equals 0, you get the a to go away. You keep the c, but we already know what c is, right? So we get 1 equals a times 0 is gone, so b times 0 plus 3, b times 3, 3b, plus, and then 0 plus 1 is 1, so it's 1 times c, which is 1/10. And so that means that 3b is 9/10 and b is 3/10, yes? And then, well, probably we just use a convenient number like x equals 1, exactly. And so with x equals 1, we get, still on the left side, 1 equals a plus b, which is 3/10, times 1 plus 3, which is 4, plus c, which is 1/10, times 1 plus 1, which is 2. And now we solve that. Let's see, we have 2/10 here. 3 times 4 is 12, 12/10, 14/10, brought over to the left side. A should be negative 4/10, which is negative 4/10. Oops. Let's see what I did wrong here. 4a is negative 4/10, because the 4 also acts on the a. And so then when you divide the 4/10 by 4, you get a equals negative 1/10. Yep, works out perfectly fine. And so that means that our fraction is 1/10 times negative x plus 3. So let's see what happens here. I want to keep the fraction out front. I kept the negative sign with the x, and I kept the plus 3 also here, right? Because a is negative 1/10 and b is 3/10. So that gives us negative 1/10 x plus 3/10 x, and I just put the 1/10 out front. And then we have 1/10, 1 over x plus 3. That one already looks all right to us. So that gives us that our integral is the integral of the decomposed function. And now we have to be careful because we have these quadratic terms here. So now we also have to split this term with the quadratic in the denominator. So we get negative 1/10 x over x squared plus 1, which takes care of this part, plus 3/10 times 1 over x squared plus 1, which takes care of the 3 here. And then we still have the 1/10 1 over x plus 3 here. And now it's a matter of recalling our integration methods. Namely, when we integrate here, we keep the negative 1/10. This is a quick substitution, which gives us a 1/2 ln x squared plus 1. We keep the 3/10 here, and then we just have to remember that the antiderivative of 1 over x squared plus 1 is the arctangent of x, and the antiderivative of 1/10 1 over x plus 3, well, that's something we do by reflex now. That's 1/10 ln x plus 3. We put the plus c in the back, and then we just realize that 1/10 times 1/2 is 1/20. Here's the answer, and that finishes out this problem. Okay, so you've seen that these computations can and do get more involved, but you've also seen that these computations remain manageable. Yes, we have to work more with fractions, but there is another educational side to that, and that is the more of this mental arithmetic we do, the more number sense we build, really. And in some ways, if you want to formulate it that way, you're also doing something for your mental health, preparing for old age, which is quite a ways away from you. But a lot of stuff that people do nowadays to train the brains of aging individuals, people in their 70s and 80s, who want to retain mental acuity, and I assure you, you want to do that too when you're that age, is that they simply work mental arithmetic with them. So, if we can already do that, we probably stand a better chance to live to a saner old age, and therefore, and also because we really need to see it all, we've got one more, and that's just about as ugly as it can get, at least when you're working with me, because here we now have a decomposition of irrational functions that has two terms in the denominator, and both terms have only complex zeros. X squared plus 4 doesn't have any real zeros, and if you look at this one also, the x squared plus 2x plus 2 doesn't have any real zeros either. So how do we set that up, and how do we solve that? And the reason why we need to look at something like that is because here, Heaviside's method just isn't going to do it anymore. We're going to have to set up a 4x4 system of equations, and if I'm sounding overjoyed, I'm certainly not, because those things are nasty, but we will see that we can solve those too. Alright, so partial fraction decomposition. What else are we going to do? We take our function, again I just call that thing y because I'll be running out of space at some point in time, and the setup is I have to have one term where this thing is the denominator and another one where I've got this thing as the denominator. So I have an ax plus b over x squared plus 2x plus 2, and I have a cx plus d over x squared plus 4, where again, as soon as you set up stuff that is quadratic, you need to have an x in the numerator also, so you will have two variables there. Alright, now the usual thing, we multiply with the denominator, which on the left side keeps us, of course, just with the numerator. On the right-hand side, well, the x squared plus 2x plus 2 will cancel here, and we get ax plus b times x squared plus 4. For the second term, the x squared plus 4 cancels, and we keep the x squared plus 2x plus 2 times the cx plus d. And, well, now, all we can do is collect terms. Okay, so the left side stays the same. We multiply out the parentheses. Let's see, ax times x squared gives us ax cubed. Cx times x squared gives us cx cubed. What do we have with x squared? Bx squared here. Cx times 2x gives us 2cx squared. And d times x squared gives us the plus d in here. And we don't have anything more with x squared as far as I can see. Terms with x would be 4ax, and then the b doesn't do anything with x's here. We get c times 2x, so 2cx, and we have d times 2x, which is 2dx here. And then we have the constant terms, which are b times 4 and 2 times d, so 4b plus 2d. So this is something, I've condensed that a little bit, on one hand also to challenge you to work this out mentally, but of course, as necessary, just write it out with some paper, and then collect terms, and you will get exactly this. And so now, as I said, Heaviside's method just doesn't lead us very far here. So now, how can you find your coefficients when Heaviside's method fails? Well, if you have a polynomial on the left and you've got a polynomial on the right, and you know those two polynomials have to be the same, then they must have the same coefficients. And that means the a plus c must be equal to the 1 that we would have in front of the x cubed. So we get a plus c equals 1. The b plus 2c plus d must be equal to 2. We get that here. The 4a plus 2c plus 2d must be equal to this 4. And the 4b plus 2d must be equal to the 10. So we just match coefficients, as that's called. So now we have to solve this 4x4 system of equations. Let's see what we can do with that. I think we'll just go to the next panel. And here is the system of equations one more time, written up in such a way that a's go with a's, b's go with b's, c's go with c's, and d's go with d's. And so now, how can we get off a few variables? We can get rid of the a's by doing the right addition here. We can get rid of the b's here by doing the right addition. Let's see what we did in the next step here. So, right, The a plus c equals 1 and the b plus 2c plus d equals 2 we just kept. And we have, if we subtract 4 times the first from the third, the 4a minus 4a goes away. 2c minus 4c is negative 2c. 2d minus nothing is 2d. 4 minus 4 is 0. So that's how we got the third equation. And the fourth equation we actually kept. All right. I mean, that's perfectly fine with me. Because now we have to eliminate the b's if we really want to go with a straight elimination algorithm that gives us a system in diagonal form. And so the next step probably is to subtract 4 times the second equation from the fourth equation. Yeah, that looks very much like what happened here, right? The first equation we keep, second equation we keep, third equation we keep, fourth equation is different, and that's because 4b minus 4b is 0. 0 minus 8c, negative 4 times 2c, right, is minus 8c. And then 2d minus 4d is negative 2d. And 10 minus 8 is 2. So this is straightforward solving systems of equations. It just takes a while, but we can do it. And so now certainly the last step in working with all the equations is that we're going to eliminate the c here. So we keep the first, we keep the second, we keep the third. You know how that goes. You have a lot of bookkeeping to do to just keep all the information around. And then here we subtract 4 times the third equation from the fourth. So let's see, negative 8c minus 8c is 0. Negative 2d minus 8d is negative 10d. And 2 minus 0 is 2. And now we just do backward substitution, right? D is negative 1/5 because it's negative 2/10. We plug that in here, and that would give us that negative 2c is 2/5, so c should be negative 1/5 also. All right, got that. And then we have negative 2/5, negative 3/5, so that would be b equals 13/5. All right, now I'm finally getting warmed up here. And a is 1 minus c, so that should be 6/5, and a is 6/5. And that means our function y, and now we just have to take that back in, right? A was 6/5, so 6/5 x plus 13/5 divided by the first one, plus negative 1/5 x plus minus 1/5 divided by the second one. That's the partial fraction decomposition for this function that we have here. Now we integrate. So we have that this big old integral is equal to the integral of the decomposed function. Now again we have to split that apart so that we have the x's and the constants by themselves. So this is, let's see, how did I break that up here? Oh yeah, now we have to be careful because there is one more integration trick for the first one. Okay, so in order to have our minds clear for that, let's first dispense with the easy one. There's a 1/5 here. I pull the negative 1/5 out front, and I just have an x over x squared plus 4 here. And I've got a 1 over x squared plus 4 here. We know how to handle those. However, the denominator for the first one, when you complete the square, and that's another skill that you will need here periodically, when you complete the square, you realize that x squared plus 2x plus 2 is x plus 1 quantity squared plus 1. And so now, in order to really do my substitutions all right, I need an x plus 1 up here, not just an x. And so that means I have 6/5 x plus 1 here, so I already took a 6/5 away from the 13/5, and that means I only have a 7/5 left, and so I've got 7/5 times 1 over x plus 1 quantity squared plus 1 left here. Make it very clear to yourself that this is the right decomposition. If it doesn't want to work out, go ahead and multiply it out and basically go backwards. Take these terms and prove that they add up to this so you can see how this decomposition takes place. And well, now we are done with the algebra part, and so now we need to integrate. And so what do we have here? Well, what we have is that this term here actually is a 1 over u squared plus 1. It is just, no, it is a u over u squared plus 1, it is just shifted because u equals x plus 1. So here's where you do multiple substitutions at the same time. You set u equals to x plus 1, and then integrate, and so you get 6/5 times 1/2 ln u squared plus 1, and u was your x plus 1 in here. Then you have 7/5 arctangent x plus 1. Well, that's not too bad because there's only u sub u substitution, u equals x plus 1 in here. And then we have minus 1/5. There should be a 1/2 from the substitution, and probably more because you'll need a 1/4 or so because you're, no, it should just be a 1/2. Yeah, negative 1/5, 1/2 ln x squared plus 4, because you do a substitution, u equals x squared plus 4 here. And then you have one where you work again with the arctangents. You get negative 1/2 and negative 1/5. Then you get 1/2 arctangent x over 2. That's one where, if necessary, it can actually be helpful to have those formulas for the integrals memorized, especially if on an exam or so you're not allowed a formula sheet, which is something that is certainly left up to the discretion of whoever your instructor is. Okay, so we have the ubiquitous plus c. And just to work out the numbers one more time, basically that's now just quite trivial. We combine the fractions, of course, so the final answer here is 3/5 ln x squared plus 1 plus 7/5 arctangent x plus 1 minus 1/10 ln x squared plus 4 minus 1/10 arctangent x over 2 plus c. And that's it. And, well, that is therefore... I'm back. That is therefore really already the end of our presentations on integration methods. We will have another class, another presentation on which integration method to choose. And, well, one choice there will be very simple. That's the choice that you want to just remember. Anytime you've got a rational function, really, all that you need to do is partial fraction decomposition. And partial fraction decomposition can get tedious, but it's not difficult in principle, as long as you are on top of your computations, and we need you to be, just to make sure that these computations don't distract from the more complicated conceptual stuff that we're going to do in the following. As long as you are on top of those symbolic computations, partial fraction decompositions will work out just fine. And yeah, other than that, truth in advertising, if/when a partial fraction decomposition gets too bad, use a computer, because that's what I do. All right, I'll see you in the next one.